Hello, everyone, and welcome to the 9th in our tutorial series. So as those of you who have, well, actually, let me introduce myself. Sorry, I'm Lee Chinitz. I am the CTO at octoScope. And as those of you who have joined today most likely know, octoScope manufactures personal test beds for wireless testing. And many of these test beds, the users of these test beds create their own tests. But a very popular technique is to use predefined tests, test suites, especially those that have been created under some sort of industry consensus. People like to know that the tests that they're doing are tests that are found to be useful by a wide variety of people. So in a previous tutorial, which was actually tutorial number 6, we described one such set of tests, which are the TR398 test suite from the Broadband Forum. So today, we're going to describe other similar tests, starting with the IETF RFC 2544, and we're going to expand the story from there. So we're honored, actually, to have as our first speaker today, Fanny Lenarski, who's the founder and CEO of octoScope. Fanny has a long history in the wireless test field, and she actually has direct experience in defining some of the test suites that we're going to discuss today. And then after Fanny, our speaker and our story is going to be picked up by octoScope's chief scientist, Steve Shearer. Like Fanny, Steve has a long history in wireless product development and in standards participation. So with that, I am going to turn the story over to Fanny.
Great. Well, thank you, Lee. Can everyone hear me? If not, send us a note. Yes, thank you, Lee, very much for the introduction and for being here to help us with the Q&A. As you folks know, we come to you live. We do it 3 times to reach all the time zones, and this is our first session. It's 10 a.m. in Boston, and we're happy to be here. We're happy you were able to join us. So as Lee pointed out, today's topic is one of the standards-based tests, RFC 2544. We'll give you a background on what this document is and how it came about. And as Lee mentioned, I actually was there. I am probably the oldest person at octoScope, and I was there in the early 1980s. When Ethernet was born, and shortly afterwards, this RFC was born when Ethernet switches came about. So we're going to talk a little bit about that history, and I need to ask you to bear with me. It's all relevant. It may seem like I'm telling you a long story, but you will see why it's relevant and will be helpful. We'll talk about a more recent specification from IEEE 802.11.2, which covers performance testing. I was also there. I was actually one of the founding members of that group at IEEE. It was TGT, and we got T for that group, task group, T for test. We were very happy about that. And so we incorporated, actually, RFC 2544, and it's part of that specification for Wi-Fi performance testing. And then Steve has some deep dive into some of the tests that RFC 2544 specifies, and some demos using the Octobox. So starting with the history, we're going to dive in. So this is ancient history, folks. Back when I graduated from college and I came to Boston for my first job, it was with Chipcom Corporation. And actually it was my second job. Chipcom Paradigm was my first job. Chipcom made Ethernet switches. But before the switches came about, we had this very ancient dinosaur age technology. I don't know if any of you are as old as I, but I actually had these transceivers, and they come connected with this big, thick, yellow coax, a special coax cable, and we had it snaked into each office and snaked out into the adjacent office. It was just laying on the floor. And the transceiver had this little vampire clip. You actually pierced the cable. There was a lead going into the center conductor to pick up Ethernet. It truly was a bus, just like this, a very primitive bus. And you had a transceiver connected to it. Now, the AUI cable here, attachment unit interface, that went into your computer. And so that's what I had. That was my first network. And when I came to work for Chipcom, the founder of Chipcom told me we were doing 10 megabit per second. And at the time, to me, it was ridiculous speeds because I just came out of school and I started with 300 baud acoustic coupler, the one that hisses at you and you stick it into the phone. And then we got up to 192K baud acoustic coupler, and that was really, really fast. It was screaming fast at the time. And so I said, 10 megabits per second, you'll never need that. You know, well, why do you need that? And well, here we are, we're pushing multi-gigabits per second through Wi-Fi now, which it's incredible that we've come a long way. But anyway, this is a technology, and it's a bus. And so this whole collision detection, CSMA, carrier sense multiple access, was born here. Because all of these PCs, computers, they weren't PCs at the time, they share this bus and they can't talk at the same time. Because if they get on this bus at the same time, they get what? A collision. So Ethernet was developed to detect collisions and avoid them, and not avoid them. Avoidance came with Wi-Fi. It was just detection and retransmission. So that's a technique that was invented for this bus. Okay. And then later came this big innovation. That was what Chipcom was doing, is twisted pair Ethernet. So we went from this big, ugly, snaking bus to, and all the marketing people who were marketing were telling us, well, you can run it on your existing telephone lines. You just plug it into a phone plate and it'll run Ethernet. Well, guess again. We then discovered a lot of these twisted pair lines were not actually even twisted and weren't adequate to run Ethernet. But we started installing, and so the cable installer industry was born. So everybody started snaking true twisted pair. Cat 5 was born, and Cat 6, Cat 7, and then my career took a turn. I went into testing, so I made the first tester for twisted pair to scan it. And anyway, it's ancient history. But twisted pair was born, and it was, instead of this bus with yellow cable, we had a shared media hub. So shared media hub, this is mostly analog. It's like a transformer-based system. And whatever anybody transmits into any of these jacks, everybody else hears, so you still maintain this bus. And in fact, if you ever see an Ethernet, when you draw your diagrams, network diagrams, Ethernet is always drawn as a bus. Even though today it's a switch. So we now use switches. So switches were an innovation on this shared media hub. And that was a big step, because now the marketing people came on and told us, now every one of your ports on this hub, this Ethernet hub, will be like your own dedicated 10 megabit per second network. It'll be your own. Why? Because we have this silicon, this new silicon called switch fabric, and that basically has a lookup table. It knows if you are sending a packet from here, where the destination address is, on which of the ports, and it will, at wire speed, route it, look it up and route it. And so this is what the switch fabric was. And of course, a lot of claims are made, and then the test equipment people come in and say, well, now we gotta validate it, right? We gotta test it. And so this was a big claim at the time, right? You get wire speed routing of all the packets. And so testers were born. The very first tester I actually used, I think I had a model of smart bits with only 3 modules. I remember buying them. And the way this tester works is it's a chassis with plugin modules, and each module connects into each port of the switch. And then inside the module emulates a station or a bus of stations. And then this whole thing has FPGAs. It's FPGAs on each module at wire speed to pump these packets. And the packet would come back to another port, from port to port, and basically test the switch fabric, okay? We tested the switch fabric, and we would beat on it. We would send very aggressive load to see if it can keep up with back-to-back minimum size frames, right? That you need to get the maximum frame rate, the smallest frames, smallest gap, back-to-back, continuous. And the switch fabric supposedly can keep up with it and not drop any packets. So this is where packet loss measurement came in, right? It's for the switch fabric. So what happened, again, history, but what happened with smart bits, it got sold to Spire. And it evolved and it became the test center. And so this test center really originated from this RFC 2544. Usually, as you know, test equipment folks are very active in creating these test standards along with the user community. And you see how it basically inherited the chassis, the modules, that kind of architecture. Ixia was not spun off exactly. One of the key guys was actually at SmartBits, who left SmartBits and founded Ixia. Ixia went competing head-to-head with SmartBits. And SmartBits was Netcom. The company was Netcom. Netcom was sold to Spire. So these two were competitors early on for switch test business. And then some folks who left Ixia later on became very wave. They brought some of this RFC 2544 into 802.11.2, but we're getting there. And then I founded Azimuth Systems back in 2002. And we also created a chassis-based system, but we went one step further, and we had completely RF isolated modules, and we had these test heads. You see these test heads, so you can put your device into isolation. Now, these guys haven't yet realized that they will need isolation, but Azimuth already knew that. And so, long story short, we worked with VeriWave in this 802.11.2 group in TGT. And some of this test methodology that was there to test switches got adopted into Wi-Fi. So why do we need it in Wi-Fi? We don't have switches in Wi-Fi. But we do have it. Each IP has routing logic, right? And it's very similar because a packet comes in on some interface. In the case of switched Ethernet, it came in on the twisted pair interface into the switch matrix. And the switch matrix had to look up the address, destination address, see which port it's on, and route it there at wire speed. Right, but in a router, in a Wi-Fi router, well, you don't have quite so much silicon power, right, as a switch matrix, but you do have routing logic, and routing logic runs on the latest and greatest processing subsystems very fast. And if you ever touch one of these modern APs, they're very hot. You can fry an egg on one of them. So they are, clicking, multi-gigahertz clock cycles through that processing subsystem. Looking up each address, it could come on the Ethernet ports of the router, it could come on the various wireless ports. Like a lot of routers today will have 3 radios at least. 2.4 gigahertz, the 5 gigahertz on the high band and 5 gigahertz on the low band. They have a WAN port, and so you have to route among all these ports. So it's very, very similar type of test. You need to know whether this routing subsystem is actually performance limiting your router, right? So as all good test people know, the good test methodology, you have to divide and conquer, because you have two things here in your access point router under test that can limit your performance. And if you're a good test person, you know that you have to separate them and test them separately. Okay, we all know that. And so we isolated the logic. So the logic part, we call it, that's the lookup function, lookup table, and shoving the packet into the right interface, right? Some of it goes to, I mean, we have 3 radios, but this is simplified, right? We have the logic subsystem, and this can lose packets, okay? And then we have a radio subsystem. Now, this can also lose packets, but differently. It will lose packets when we start putting attenuation, multipath, interference on the radio interface. Totally different mechanism for losing packets. But both lose packets, but you have to, when you're qualifying this router, you need to isolate them, test one at a time, so that you can isolate the root cause of where your packets are lost, so you know where to go fix stuff, right? And then you can put them all together, but now we know a lot about it. So we have this radio logic, we have all these endpoints. Endpoints could be iPerf endpoints. In the case of octoScope, we have multi-perf, which are managed iPerf endpoints, and there's more than just iPerf in there, but managed, out-of-band managed, and so there's a lot you can do with that. So far, so good. Any questions, folks? As you know, we're here live, and there are several very smart people here, and we can take your questions anytime. All right, terrific. So let's keep going then. And so how do we test it? We basically, what do we measure and how, okay? So we basically shove packets at it, okay? And then see if they come out of the right port. And we have to beat on this port device under test from all the ports it has to all the other ports. That's what the smart bits invented. They invented that methodology. Very cruel, I know, but that's what gives us good, fast networking. That's why we can be on Zoom today. So what do we test? We test throughput. We test packet rate. How fast can this device under test? Whether it's a switch, Ethernet switch, or a router these days, how fast can it process these packets? Packet loss rate, how many it loses? And latency and jitter are very important for some real-time applications. Skype, Zoom is one of them, right? If we start losing packets or we have latency, my voice is going to sound very strange, and hopefully it doesn't. Hopefully it comes across well to you. And thanks in part to all these test people. We test this stuff and we make sure it works. But anyway, so these are the tests. We have to measure it. And we do it versus packet size. So for like lookup function and routing, the most difficult test is minimum packets, minimum IPG, it was called in Ethernet world, IPG, interpacket gap. And so that's the highest packet rate. So if a routing subsystem is gonna lose packets because it can't keep up with this rate, because for each packet it has to do work. It has to open the packet, look at a header, look at the source and destination address, do a few things, find it in the lookup table, and put it in the right port. And that requires a buffer, memory buffer management. So there's a lot to it, and so this is the most aggressive test. And then we do it at maximum throughput. So this is maximum packet rate, smallest packets. And it's actually pretty low throughput, but it's still a ton of work for the router. So, and in the Wi-Fi industry, we're used to looking at throughput. And when folks are starting to do packet rate tests, they see this minuscule throughput and say, oh my God, you don't have any throughput, what are you showing me? But it's actually a lot more work for the router to measure it without to actually process the stream without dropping packets. But maximum throughput obviously is when we have the most bits on, the duty cycle of usage of the air link. We have maximum packets with minimum gaps, so we maximize how active we are on the air link, and we then transmit maximum megabits per second, right? So this is where we get these megabits. And this is also challenging because for the processing subsystem, it's just a different challenge. You have plenty of time to do the lookup and routing because you have this long packet. But then you have to manage buffers. It has to chop up this packet, put it into memory buffers and do it quickly, and then read and write it quickly. So you can have other bottlenecks, other processing bottlenecks. And then, yes?
Oh, I'm sorry, there is a question that came up. Somebody is asking what would be the acceptable packet loss ratio for a practical Wi-Fi deployment scenario, and what would we recommend?
That's a good question. 0. I would say we have, and actually Steve has a really good demo. So packet loss is actually managed by TCP IP. TCP has flow control built in on layer 3. So it will, if it senses that their packet's lost and it gets acknowledgement on layer 3, it will throttle back that stream. But for real-time applications like Zoom, like voice, we typically use UDP or RTP, some other non-TCP mechanism. And then, and especially if it's multicast, right, we just don't have a way to manage flow control to multiple points. So this is broadcast, multicast. Then the packets just flow, and that could be UDP, RTP, whatever. We don't worry about flow control. And that's when you see packets being dropped, right? And so that can be managed, and that we have to measure what is the rate of packet loss. Now, so the rule of thumb is if you have a certain PHY rate, that's physical layer rate, right? Let's say we're transmitting at 1201 megabits per second on the PHY, which means on the MAC layer, we cannot go any faster than that. We cannot possibly go any faster than that because that's our physical layer rate. Then at that offered load, and Steve will explain what that means, that's basically the rate at which we send these small packets to the router. It should be able to keep up with 0 packet loss rate. That's kind of my answer. I don't know that whether the standards have pass-fail guidance. I don't believe so, but we can leave that. Steve or Lee, do you guys know whether RFC 2544 has any limits?
So they normally they search for that point where the packet loss rate is actually 0.
0, right, and that's the result. So then when you're comparing these routers, A, B, and C from different vendors, you can see where 0 packet loss rate is, and it will be at different points. Yeah, and that standard was used to run competitive tests like that.
Yeah.
All right. Okay, so we have a range of packet sizes because when vendors started optimizing for minimum, then optimized for maximum, then the test people, if we're good, we find these things. We found that at minimum, medium size, there were issues for other reasons. So anyway, so there's a range of packets, and we plot these results, let's say throughput or packet loss rate, or all of these metrics versus packet size on the x-axis. Okay, so what happened is the folks who came from Ethernet world, including me with Azimuth and Variwave, we took this test methodology and incorporated it into 802.11.2 when we were working at this TGT together. And this standard is actually recommended practices document was published in 2008. This is a very comprehensive, nice document. A lot of smart people put a lot of work into it. It specifies a lot of stuff that deals with wireless itself, not just the routing subsystem, but a lot more than that. There are environments, for example, different environments, and you measure like a long list of metrics in different environments. So some of them we've done forever in a test house running with a car, and then indoor, outdoor, and then there were some of the they called calibrated over the air. That's essentially the Octobox type of environment. Can be conducted, can be over the air, or both. Right? So different environments, a long list of tests. So we just summarize the test cases as their group, but within each test case, as in any test standard, there's a lot of nuances. You could break each of these big test cases into dozens of different variations, like versus different channels, versus different interference scenarios, channel width, .11 generation standard, etc. Right? So this explodes into a lot of test cases, but it's a very comprehensive list. So you can see everything that's important for Wi-Fi is in this leftmost column, 802.11.2. And the contribution from the Ethernet days is here. It's basically a subset of these tests. These are important tests because this processing subsystem will throttle your throughput, and you need to know that where that impairment comes from, whether it's your radio or it's processing. And so that's what these tests give us, okay? And so obviously we do them all. We've created the standard back under Azimuth, but doesn't matter. And so, so this RFC, why do we do it? Well, it's important. I already mentioned Zoom, obviously, it's real time. You guys want to hear my voice. I want to hear you asking me questions. And so you need, similar to voice, but voice not the only, there's gaming, there's video conferencing. Packet loss rate is important. If you lose, for example, a burst of packets, you will hear a click in my voice. So, random loss is not as bad as bursty loss. So there's some nuances up for that. Jitter, obviously, the codec that actually creates the voice signal out of these packets that arrive to you to your PC. There's a coder decoder codec device that takes all these. My voice is chopped up obviously into little packets, sent over the Ethernet. They come in, they have to be reassembled by the codec, and my voice is created back to you. But if I have jitter, then it doesn't know the sequence of these packets. If jitter, which is delay variation from packet to packet, gets really bad, then my voice will suffer. You will not be able to recreate it. So packet loss, delay, and jitter are important metrics. And that's what this RFC 2544 invented those metrics for us, and we use them today. And so with that, my part of this tutorial is done. I can hand it off to Steve, but before I do, I'll just ask if there are any more questions.
And there is one question on here now. The question is, what's the relationship between 802.11.2, RFC 2544, and Wi-Fi certification?
Good question. So Wi-Fi certification does not do performance tests. It really measures interoperability of different chipsets. And we actually have some good tutorial on that, but that's the goal, and that's why the Wi-Fi Alliance testbed has in it devices with every chipset that's on the market. So these devices are part of the testbed, and when you want to certify your device, we test interoperability with every other chipset that's out there. That's oversimplification, but there's no performance testing. The difference with RFC 2544 and IEEE 802.2, they both are performance test documents. That was the goal for these documents.
One more. When do we expect an updated version of Tier 398 for 802.11ax? I guess I'll take that one. That's okay to do that now, right? You're okay with that? Mm-hmm. Oh, yeah. So Tier 398, the answer is soon. Tier 398 group just finished its Q3 virtual meeting And there is what they known as issue 2 for TR398 is written and is out for straw ballot. People will be voting on it early October. There's a meeting of the group late October, and fully expect that what is written in there right now will become issue 2 not long after that. I don't know exactly the time frame, but sometime between the end of October and probably the end of the year. Those tests do contain 802.11ax functionality. It's basically been added to all the existing tests, almost all of them. And then there's a few additional tests added as well.
All right, terrific. Well, I'm going to stop sharing and let Steve take over.
Okay, excellent. Thank you. So I'm going to talk a little bit more about 2544. I've got a couple of demos to show you, and hopefully this will just put some kind of a practical framework around it. As we've heard from Fanny, 2544 was developed in the late 80s or 90s. Its primary focus is throughput and frame loss rate. She's talked about back-to-back frames. There's an aspect of latency that's important. There are a couple of other tests which I'm not going to cover. But just worth reminding, most of the internet is based on IETF RFCs. These are not actually standards. They are requests for comments, but they are extremely useful documents, and they're widely accepted in many different areas, including, of course, Ethernet switch performance. So again, just a reminder, 2544 was invented to check out the Ethernet switch performance. There's no mention in there of any radio performance. So, and this is the reason why these standards evolve. So as we mentioned, 2544 is focused on the switch subsystem. Really, to hammer that hard, one tends to look at throughput for minimum frame size. When we start looking at Wi-Fi, in the Wi-Fi community, we prefer to report maximum achievable throughput, and very often this is done with large packet sizes, and we all know about aggregated MPDUs and all of these kinds of things. So there's a sort of a difference in kind of nuanced difference in there. Let's look at how packets can be lost in the system. In this case, for 2544, we're really focused on this routing logic. So the routing logic, as Fanny explained, has lookup tables, it has buffers, there's computation that needs to happen in there. And that's the thing that we want to check out. So we make sure that the Wi-Fi link is set up in a way that the frame error rate is as low as possible. So we want to conquer and divide and conquer. And that allows us to put a traffic generator onto the device, vary the offered load, look at packet loss, and so on. So our objective is really to measure the performance of this routing subsystem. If we apply an offered load that's too high, the packet loss will increase because there's simply nowhere for the packets to go, and we'll start losing packets. So we'll back off the offered load to a point where the loss rate is pretty close to 0. And that will give us an idea of how we can actually use the system. So I'm going to run a demo for you here. This is what the practical system looks like. In the top chamber, we have an access point. In the lower chamber, the lower chamber is a PAL box. Actually, there are 16 individual stay PALs in there, but we're just going to connect to one of them. So let me bring this across. Now, so we're connected from the access point to the stay PAL. I'm going to run this test with an offered load of 200 megabits per second. So I know that that is well below the fire rate, and I fully expect a 0 packet loss. Then I'm going to run it with an offered load that's well above the fire rate. And we'll look at the packet loss there. And then I'm going to try and set the packet loss rate to just about the point where we get 0 packet loss. I've just set these up like these so that I can do it as a convenient demo. So I'm going to start this running. As you'll see, we are connected to the first guy. We are well below the fire rate. We have 0 packet loss. We are running at a reasonably high MCS. Everything looks pretty stable here. So now I'm going to switch in the stay PAL with a much higher offered load. And you'll see that the throughput rises, as you would expect, because we are giving it more load. But you'll see that the packet loss increases. So we're at about a 30% packet loss, and that would be unacceptable. So now we want to find, a reasonable operating point. So I'm going to kick in now the third guy, and here I've previously set it to be 990 megabits per second. Actually, it's a little bit less than what we're achieving at the moment, but I think it'll demonstrate the principle for you. So now I've kicked that guy in. We are getting above 900 megabits per second. Our packet loss rate is 0. And if I wanted to, I could go in and tweak this value a little bit. I might even just do that right now. We're going to have to stop it and start it. But yeah, so here we go. And here we see, some small packet, 0.1% packet loss, 0.04% of a packet loss. And this is where we kind of zero in on that kind of safe operating point. So I'm going to stop this at that point.
Steve, we do have a question. They're asking, what kind of traffic are used for the demo, and what are the other reasons for packet loss?
Okay, yeah, thank you. So I am using UDP, and UDP is many people call fire and forget protocol. Unlike TCP, TCP has a feedback mechanism with acknowledgements and the ability for retransmission if packets don't get through. UDP, as I say, people call it fire and forget. You send the packet, you assume that it gets to the other side, and that's why it's important to not fire those packets faster than your device can actually handle. All right, I'm going to pull this out of the way. So we had a look at that. In our, so that's one way of finding the maximum throughput. In our octoScope test beds, we actually implement two separate networks. We have a traffic network, obviously for traffic delivery, but we have an out-of-band management network, and we use that to control the devices. We use that to pull statistics from the devices, and in the case of throughput, we use that to measure the throughput directly. So essentially, we count the packets per second, multiplied by the packet length, and we can get a measure of throughput directly, or as some people term it, goodput. We can also look at one-way delay. So one-way delay and jitter are important for multimedia transport. These again are touched on by various RFCs. One-way delay is RFC 7697. Interestingly, it's a fairly recent RFC, came out in January 2016 and superseded the older one that has been around for quite a long time. One-way delay is, the concept is pretty simple. The transmitter has a packet of data to send. It timestamps its departure time, sends it across to the receiver. As soon as the receiver gets that packet, it looks at its own internal clock, determines the arrival time, and then obviously the difference between the departure time and the arrival time is the time that it took to get from A to B. So this is the so-called one-way delay. The thing about one-way delay is that you obviously need accurate clocks on both the transmitter and the receiving end. And we use a PTP or IEEE 1588, so that actually all of our measurement instruments are synchronized to that, and that allows us to measure this one-way delay, both in the uplink and in the downlink. While we're doing that,
Steve, sorry, quick question.
Sure.
Question is whether the NIC card buffer plays any role in the packet loss.
Yes, indeed, it does. That's really part of when we talk about this. I'm just going to go back to here. When we talk about the routing logic and the buffer, that's all part of that. And essentially, if you're pushing packets into that routing logic faster than they can get out, that's essentially what happens. That's really that's definitely a mechanism for losing packets. Okay, so while we're measuring one-way delay, and since we are, time stamping these packets as they come in, it's a convenient point to measure jitter. So jitter is the time difference between the arrival times of these packets, and there's an RFC that covers that. So I'm going to show you a demo here that takes a look at 4 of these. At 4 of these key performance indicators. We're going to run it for a number of different packet sizes, and we're going to take a look to see how packet size affects the performance of the system. So we'll get this going. We're looking at a packet size of 64 now. We're going to run this for 5 seconds. It's going to tell us the throughput, the jitter, the packet loss, and the uplink latency. So we're looking at about 2.2 milliseconds of uplink latency. We're on to a packet size of 256 now. You'll see that the throughput is much better, and this is because there's less overhead. There's more data relative to the overhead of these packets going over the air. So we're getting to 1460, 1470. You can see a general trend there in the throughput, but we'll take a look at the graphs once they are provided. All right, so we've done that analysis. We've produced a PDF report here. And let me just blow these up a little bit more. Even go to here. So here you can, here's a plot of the throughput for the various packet sizes. You'll see the throughput's pretty low for small packet sizes. Again, we talked about protocol overhead and so on. One-way delay is pretty much constant in this case. And just playing around with this software, one can balance one-way delay versus maximum throughput. So if you set large buffer sizes, you can actually get better throughput, because although you're putting 64-byte packets into the buffer, we use this aggregated NPDUs, and then we get much more efficient transfer over the medium. But of course, what happens there is that your one-way delay increases substantially. We're looking at jitter, a very little jitter here, I would say 0.01 of a millisecond jitter, and our packet loss is very low as well. So this is a kind of a canned measurement that can be run pretty quickly to determine some of these key aspects. So I'm going to pause at that point. Any questions? I'd be happy to try and answer them.
There's nothing in the Q&A at the moment, but if anyone does have questions, let us know. I think you can raise your hand if you'd like to actually ask the question directly, or write it down. Okay, I've got another demo for you, and this is looking at something called average latency. So average latency is actually defined as round trip delay. So this is the delay from the sender to the receiver and back again to the receiver. So we're all pretty familiar with ping, and this is in fact what ping measures for us. So it's a pretty convenient way to look at both the uplink and the downlink latency. You cannot really distinguish where the delay lies, whether it could easily be greater in either the uplink or the downlink, but at least you can get a sense of the round trip delay. In this demo, I'm going to be using 8 simultaneous links. So I'll have 8 stay pals in that pal box that I showed you earlier. Here's a look at the practical system.
we have the AP in the upper box. He's going to be connecting to you know, a bunch, 8 of these stay pals down here in the PAL box. These stay pals are all going to be pinging, so they'll be sending probes up to the AP. The AP is going to be relaying those back to the stay pals, and each stay pal will record its own round trip delay. So with that, I'm going to bring my demo in. I do need to do just a little bit of setup here, so if you could just bear with me, I'll get through this quite quickly. But we're actually doing quite a bit of kind of reconfiguration. So I just want to make sure that this is all set up correctly. Okay. So here you'll see in the under the traffic pairs, I've got a bunch of stay pals here. They're all connected to the access point. If I open these up, you'll see that they're all doing ping traffic, and we are going to get started here. So this is primarily going to look at how OFDMA affects latency. OFDMA is purported to be very good in dealing with short packets, which legacy Wi-Fi is not. And one of the advantages of that is that it can deal with these short packets very efficiently, and it can minimize the latency. This is particularly so when one has contention on the channel as well. So I'm going to run this. I do have OFDMA switched off, and I'm going to get this guy going. So he will take just a little time before the results come in. Here we see the results in the top window here of the round trip delay for all of the stay pals that we've got connected. So we're looking at you know, 60 or 100 milliseconds of round trip delay. I'm going to go into the PAL 6 now, and I'm going to switch OFDMA on, and we'll take a look to see what happens here. So there'll be a pause. It is sending down the configuration to the access point. It's offline here at the moment. It's just starting to come back. We'll see the devices start to associate. There's an initial delay here because of the buffered pings. I'm just going to remove this guy because he's messing up the scale. And now you can see there's a really very distinct difference between the round trip delay with OFDMA off. And as soon as I switch OFDMA on, it improves the situation substantially. So I'll pause there and see if...
Not yet. At least I'm not seeing any questions. I guess your explanation is crystal clear.
Actually, there are a couple of interesting things to just take a look at in comparing this on and off stuff. If you look at the things like the MCS and the data rate and so on, it's pretty much a mess with OFDMA off in the first half of this graph here. Switching OFDMA on has the effect of effectively bringing order to the network and bringing that order to the network, kind of scheduling in a way, really neatens up a lot of the activity. It's much less chaotic. Okay, so I think I can minimize this. So we're gonna just change gears.
We do have a question, Steve.
Oh yeah.
The OFDMA on-off feature is not available in every AP. How do you test if the feature is not there?
Sorry, I beg your pardon. Could you just repeat the question for me?
Sure, we're asking the OFDMA on-off feature is not available in every AP. How do you test if the feature is not there?
Oh, interesting question. Let me think a little bit. So certainly in all of our test instruments, that's readily available. We can just take a quick look here. So we have these little checkboxes that allow you to do that.
I think a quick way of getting at it, if you really don't have access in your DUT and you do want to try and get a sense of what's going on, would be to test in AC. So AC would clearly not have it, and then AX would. You'll have the issue of the different MCS kind of mixing in there. But that is one way you could look at the difference.
Yeah. From what I have seen, most of the off-the-shelf APs that I've seen do give you some level of control on that. But if you really don't have access to that, then I think Lee's explanation is pretty good. Okay, so so one of the other kind of evolutions I think one can say is the depth of reporting that we generally do today in the Wi-Fi industry. Back in the early days of 2544, the reporting requirements were very simple, very limited. It really amounted to sort of a table of a bunch of numbers, and that's pretty much what it was. You can look in the RFC. You know, things may be expressed, should make measurements, and so on. As the industry has evolved, we know that we need to look at a lot more than just throughput numbers. We need to be able to get a much better analysis of what's actually happening in the system. With our test beds, we actually record literally a bucket load of KPIs. They're all stored in a database. We can produce these reports so that you can take a look at them later. So we have many ways to visualize that data, and this, I think, is pretty much a general evolution in the Wi-Fi industry. So just in conclusion, Wi-Fi testing has a lot more dimensions than Ethernet testing. We really haven't touched on many of those in this talk, but we have in other tutorials. We've got to deal with motion, we've got to deal with interference. There's a whole dynamic adaptation stuff that's going on. Beamforming, OFDMA, many of these new technologies in 11AX. So this is an interesting topic. 2544 was created for switch testing. 11.2 is a more comprehensive specification that looks at Wi-Fi performance, radio performance. I put this up here just as a list of previous tutorials in case anybody wants to refer back to them. We've run quite a reasonable sized series of these, and so I put these links here for you if you'd like to go back and look at those. I'll just put out a teaser here. Our next tutorial is going to be on mesh networks. If you have any particular questions or particular aspects of mesh networks that you'd cover, drop us an email to info@octoscope.com, and we'll try to incorporate those questions or viewpoints. So thank you very much for listening. If there are any other questions, I'll be very happy to try and answer those for you.
Yep. Okay, so that being said, I think yeah, we've definitely come to the end of the hour. If you do have questions, the email address is on the screen right now. Feel free to send them to us. We will probably be reaching out, contacting people just to get some feedback on this as well. The material itself is available to anybody who wants it, and the video of this will be posted along with the rest of our videos, so you'll be able to review it again at your leisure. Again, thanks very much, and we will see you next time.